Welcome to a video on op-amp DC imperfections. In this video we will have a look at the DC imperfections more over the input offset voltage and the input bias and offset currents. So in each of these we will look at how to calculate the DC offset that will be imposed on a non-ideal circuit and how to counter these effects. And then lastly, we will look at how to build inverting amplifiers and non-inverting amplifiers, countering for both effects. So after each section, I will be doing a simulation to show you what it will look like in the lab if you were to encounter any of these problems. So first of all, we need to remember that op-amps is non-ideal devices. Okay, the internal workings of op-amp is CMOS devices, BJTs, or bi-CMOS devices. So they all need biasing currents and voltages to have them working. Okay, so all of that stuff in the beginning of assuming ideal op-amps is just to help you to get the transfer functions of op-amp. Now in a lab situation, or if you're doing simulations, you will encounter issues with your amplifiers. Okay, so how do we see these issues and how do we counter these issues? Okay, so as a model for the input DC offset voltage, we can take our ideal op amp and just put a voltage source at the non-inverting terminal and use that as our model for the offset voltage that is internal to the amplifier. Now this is typically not a very large value, but when we apply feedback, this is amplified by our amplifier. So non-inverting, inverting configuration doesn't really matter. In the inverting, our input would be here. So if we ground this, or the non-inverting input this side, ground this, so basically ground both terminals, we would see that this DC source in our model is being amplified in a non-inverting configuration. So this is only 5 millivolts internal to the op amp. For a gain of 101, this can go up to 505 millivolts. So half a volt of offset on your output. Okay, so if you're trying to have rail-to-rail applications, it will saturate much sooner on the top rail than at the bottom rail. Okay, so it will start to clip. So how do we get rid of this DC offset right here? So first thing is, this is all due to the amplification. So if we can get the amplification out of the equation, we will be kind of set. So if we add a capacitor on the input here, DC can't flow that way. So in terms of a DC source like this resistor 1 and capacitor isn't there, it doesn't exist. So for this 5 millivolts as an offset, this amplifier configuration looks like a buffer. So this 5 millivolts will be sitting on V out only. So instead of amplifying this 5 millivolts with 101, it is just now placed at the output. So from 505 millivolts to 5 millivolts. Okay, so the thing to consider is this capacitor is working like a high pass filter. So I just added the 1 microfarad in here, and this means that frequencies below 106 Hz will be affected. And this amplifier can't be used to amplify DC signals anymore. It is AC only. So let's have a look at a simulation of all of these effects. So I have set up this amplifier firstly with all the inputs grounded so that we can see the output offset. Then one with a sinusoidal input and one with the capacitor countering the DC offset here. So if we run this simulation, I'm going to first look at this amplifier. So if we run this and we take the output, we would see that we have roughly 505 millivolts on the output here from this DC source right here. Okay, if we have a look at the one with a sinusoid, our sinusoid is being offsetted by this 505 millivolts. And if we're going to have a look at one of the capacitor, this has been moved downwards. But you can see that there is still a bit of an offset on this, which is that 5 millivolts right here. But the big offset has been removed. So here's the original signal without the cap, and here is the signal with the capacitor. Okay, so next I'm going to have a look at some DC simulations. So just do a DC sweep. So if we run the DC sweep, we will see for this amplifier, the output is just straight for 505 millivolts. For the last one, our output is the 5 millivolts, straightforward. Okay, and the one here in the middle, also remember for a DC sweep with a cap on the input, the output will always be whatever is going on the inside, because that variation of a DC voltage does not enter this amplifier due to the cap. And if we have a look at this one over here, we can see our output ranges. So it's perfect for this amplifier because it's an ideal amp that we're using. And we can see our input range. But if we look here around 0, 0, we will see that our signal is not passing through 0, 0. So at 0 volts, we see an offset of 500 milli. And if we have a look at our signal at 5 millivolts, here in between, there our output is 0. Okay, so if I just do this second DC simulation, I have made the range a bit smaller. We can see this kind of nicely. So here at 5 millivolts, our output is at 0. Sorry, here. And at 500 millivolts output, our output is right here. Okay, so you can use DC sweeps in simulation to kind of find the offset input and the offset output. That is a very nice way to find these. Okay, lastly, if I quickly do an AC simulation, let's do this AC one, run it, have a look here. There is no low frequency cutoff. And if we look at the one with capacitor, here at about 160 Hertz, there is our minus 3 dB point. So adding the capacitor does influence our frequency response. So remember that when choosing a capacitor size here, the larger you go, the closer this will go to our 0 or DC point, where the baud plot does not account for DC. So yeah, just keep that in mind when adding the cap. the input bias and offset currents. Okay, so for our ideal op-amp, we assume that the two currents flowing into this op-amp or out of this op-amp, depending if it's NPN or PNP based. For CMOS, those currents are non-existent or in the picoampere range, so nothing to worry about for CMOS. But this is mainly a problem for BJT devices. For the ideal case, we assume that this is 0. Now, this is not 0 in practical op-amps. And these two currents are close to one another, not exactly the same. So what happens if we apply feedback to our system or put this in an inverting configuration? So, before I get started with that, a couple of definitions. Input bias current, if you find this in a data sheet, this is the average between these two currents. So IB is the one that you'll typically use in your calculations. The offset current is the difference between these two currents. So that slight difference that you get is the offset current. Okay, so let's assume we ground our V in. This non-inverting terminal is already grounded. This means that IB2 is technically non-existent. So we will have currents flowing towards IB1 here as the current source. Okay, and if we have currents flowing through resistors, we get a voltage, and that voltage will be translated directly to our output. So to calculate this, our output offset voltage is IB1 times R2, or roughly IB R2. Okay, so if this bias current is 100 microamps, we could have up to a 1 volt offset at the output. That is quite a lot. Now, how do we counter this effect right here? Since this is causing a voltage, if we utilize the second current source right here and also apply a resistor to it, we can create similar voltages at the two inputs and have them subtracted. Okay, so this current source causes a voltage and this current source causes a voltage, and if we can have a voltages equivalent, we can get rid of the output offset voltage due to this. Okay, so since the current of IB1 is flowing through both R2 and R1, we can apply a parallel combination of the two in the position of R3. Okay, so now they can create similar voltages and be subtracted. Okay, now since the two current sources is not the same, the output offset now will be the offset current multiplied by R2. So in the case where they're like 0.1 microamps apart, the offset will now be just 10 millivolts instead of a 1 volt that we had. Okay, so the first counter is by applying a resistor down here, which is equivalent in size. This has no effect on our input to output ratio. So this has no effect with the gain that we had. Right. Now, in the case where we already applied the capacitor to counter for the offset voltage, this resistor now does not exist anymore to the DC current here. Okay, so there is no current flowing here. We only have a current flowing through R2. This means that R3 should be exactly the same size as R2. So R3 is R2, and then the voltages will be equivalent and subtracted. Okay, so note also if IB1 and IB2 is exactly the same size, then the output offset will be at a 0. Okay, so just if they were perfect, this will be a 0 when you apply this resistor right here. If not, you will still see the offset. Okay, let's jump to a simulation of this. So I set up two equivalent circuits, and the additional resistor I step between 1 ohm and 199 ohms. So the 1 ohm is when it's just a wire, and the 99 is when we're countering for these currents. So the first one gets a DC input of 1 millivolt, and the second one gets an AC input of 1 millivolt peak. You can see that there is an imbalance between the two current sources. They are roughly equivalent. So if you run this simulation, and let's click on the first one, the blue graph here is with our countermeasures added, and this green one up here is without. So if we insert 1 millivolt DC, we would expect this to have a minus 100 millivolts out. Okay, so with the countermeasures employed, you can see that this is roughly minus 100. And in our calculations, we have a 1 volt offset here. So 1 volt minus 100 milli would be 900 millivolts. Okay, same for this side of a sinusoidal input. With our resistor added, our signal is moved downwards, and without, there is 1 volt offset on it. So if we zoom in here, we will see that this is at about 90 millivolts, and this is still a bit less than 90 millivolts. This is more or less 100 or minus 100 millivolts. Okay, so there is still an offset being added due to the imbalance in these two current sources. So if we fix that, take a bit more signal, you will see that these circuits are now more balanced. Okay, so adding this resistor removes the DC offset, and we will only see the effect of the imbalance between these two current sources. So I quickly went ahead and added a third simulation where I have this resistor constantly at 990 ohms, and I change this current source from 10 micro to 10.1 micro to 11 micro. So there's a big difference between the two. There will be a big offset, small offset, and no offset. Let's run this, have a look at the output, and you'll see that the one there is the perfect signal. one with only iOS multiplied by R2, and then the huge offset here at the bottom. Okay, these offsets are influenced by the size of resistor 2 right here. So please try and keep your resistor values small. Okay, that will also limit the offsets. Now we will have a look at the inverting amplifier and how do we counter both these imperfections at the same time. So here I set up an ideal amplifier with a offset voltage and two bias currents with an offset between them. And in the simulation we can have a look at both, and in here we countered firstly for the DC offset voltage, so there's only 5 millivolts being added here and 10 millivolts extra for our bias current counter of this resistor. So you need to add both the cap and the resistor to counter for the huge offsets that you can have. Let's run this. And if we have a look at this, our output should be 100 millivolt sinusoid, and we have 1.5 volt of offset here. So half volt from our offset voltage and 1 volt from our bias current. So adding the resistor and the cap, we have roughly our 15 millivolts of offset, and you can see that our signal is being amplified here, but most of the offsets have been removed. Okay, again adding the capacitor will have an influence on our low frequency side, and if we take this one, there is no influence on our low frequency side. So for the inverting amplifier, you have to add the capacitor and the resistor. Now we will have a look at the non-inverting amplifier and how to counter both DC imperfections at the same time. Here I have our non-inverting configuration with our offsets and bias added. And to counter both effects, you need to add a capacitor to this resistor over here so that this DC voltage is not being amplified by the amplifier itself. Okay, you need to add the resistor for the DC bias countering, and you need to add additional capacitor on the input so that no DC voltages can come in and affect any of our circuitry here on the input side. And remember that this ground path here is extremely important to maintain, or else this amplifier will not be biased. Okay, so you cannot have this capacitor here on the non-inverting configuration without having the resistor. So let's run the simulation and see. Here we again have a 1.5 volt offset, and here most of the offsets have been removed. Okay, so the non-inverting configuration has a bit more components to counter for the DC offsets, and this resistor here, even though that it's there to help counter the DC biasing, it is also a DC ground path for our amplifier. So if this resistor is not here, this amplifier will not work properly. especially with this cap included here. So that is very important. Okay, let's have a look at the AC characteristics. Run it, AC, and again the low frequency is affected. That is it for the DC offsets, DC characteristics of our op amps, and how to counteract the negative effects that it will have in a circuit. Thank you for watching.